Two spacecraft launched in 1977 are still sending messages to Earth from interstellar space. Voyager 1 is more than 25 billion kilometers away. Voyager 2 is more than 21 billion. Each transmits with roughly the power of the small bulb inside a refrigerator. By the time that signal reaches Earth, it has faded to less than a billionth of a watt. A digital watch uses about 20 billion times more power. By every ordinary intuition, that whisper should disappear completely. It does not. Across 3 sites around the world, enormous antennas turn toward the precise point where each spacecraft should be. They listen through hours of static, isolate a signal almost indistinguishable from noise, and recover information transmitted nearly a day earlier. This is how we are still in contact with Voyager. By the end of tonight, you'll understand how Earth catches a signal that weak, how engineers still command computers built nearly 50 years ago, and why the conversation must eventually end. If you enjoy stories like this, take a second to like and subscribe. It really helps the channel. Now, let's begin. The conversation still reaching Earth today began with a discovery made 13 years before either spacecraft left the ground. The year was 1964. Gary Flandreau was a summer student at the Jet Propulsion Laboratory, doing the kind of unglamorous trajectory mathematics nobody expected to change the future of space exploration. He had not been asked to search for anything extraordinary. He was simply tracing where the outer planets would be, year by year, decades into the future. Then he noticed something unusual in the numbers. Jupiter, Saturn, Uranus, and Neptune were approaching a rare alignment. All 4 outer planets would be positioned in a way that allowed a single spacecraft to swing from one to the next, using each planet's gravity to accelerate toward the one beyond it. The opportunity would not return for generations. NASA and JPL placed the cycle at roughly once every 176 years. Flandreau remembered calculating 175. Either figure tells the same story. Miss this alignment and the next one would arrive more than a century and a half later, long after everyone involved in the mission was gone. Flandreau published the idea in 1966 in a paper titled Fast Reconnaissance Missions to the Outer Solar System Using Energy Derived from the Gravitational Field of Jupiter. The title was dense. The idea beneath it was simple. Use Jupiter's own motion to throw a spacecraft toward the edge of the solar system. That maneuver is called a gravity assist, and it works almost like theft, except nothing meaningful is taken. A spacecraft approaches a planet that is already moving rapidly around the sun. As the craft falls into the planet's gravity, it accelerates. If its path is angled correctly, the planet bends the spacecraft around itself and sends it away in a new direction with greater speed relative to the sun. Imagine rolling a ball into a valley and watching it climb out the other side. From the valley's perspective, the ball gains speed as it falls and loses that speed again as it climbs. Nothing appears to have changed. But now imagine that the entire valley is moving. The spacecraft leaves carrying a tiny fraction of the planet's orbital momentum. Because the planet outweighs the spacecraft by trillions of times, its own motion changes by an amount too small to measure. The spacecraft's speed, however, changes enormously. A tiny machine borrows motion from a giant world, and the world never notices the loan. The gains can then be stacked. Voyager 2 gained about 10 kilometers per second at Jupiter, another 5 at Saturn, and roughly 2 more at Uranus. At Neptune, it deliberately surrendered some of that speed, so its trajectory could bend close to the distant moon, Triton. A direct flight from Earth to Neptune without those assists could have taken around 30 years. Chaining the planetary encounters together reduced the journey to 12. The plan made possible by Flandreau's mathematics was ambitious almost to the point of arrogance. NASA proposed 4 spacecraft launched in pairs. One pair would travel past Jupiter, Saturn, and Pluto. The other would visit Jupiter, Uranus, and Neptune. Together, they would survey the outer solar system in roughly 7.5 years, instead of the 13 or more years required for one spacecraft to attempt everything alone. NASA called it the Grand Tour. For a while, it appeared that the mission might happen exactly as imagined. Then, in December 1971, the budget collapsed beneath it. Congress wanted the money directed elsewhere, and the developing space shuttle program was consuming resources that 4 interplanetary spacecraft would have required. The proposed Grand Tour was expected to cost between $750 and $900 million, with roughly another $100 million needed for launch vehicles. The mission could not survive that arithmetic. Not 4 spacecraft, 2. The project was scaled down, stripped of much of its original ambition, and kept alive just barely enough to take advantage of the planetary alignment. In early 1972, NASA approved the replacement under the name Mariner Jupiter-Saturn. It would later become Voyager. The 2 spacecraft were built almost identically. If one failed completely, the other could still deliver the mission's essential science at Jupiter and Saturn. Redundancy was not simply designed into the individual machines. It was built into the existence of the second spacecraft. Each also carried something unusual bolted to its side. A golden record intended to speak for an entire species. But that part of the story comes later. On August 20th, 1977, the first spacecraft launched. It was a Voyager 2. Its trajectory was slower and more patient, preserving the possibility that it could continue beyond Saturn to Uranus and Neptune if the spacecraft remained healthy and the funding survived. 16 days later, on September 5th, Voyager 1 followed. It was placed on a faster, more direct route designed to reach Jupiter and Saturn first. The numbering does not match the order in which they launched. The reason for that mismatch is also the reason the 2 spacecraft eventually lived such different lives. Voyager 1's path was aimed for one specific target, a close pass by Saturn's largest moon, Titan, at a distance of about 4,033 miles, roughly 6,190 kilometers from Titan's center, threading behind Saturn's rings on the way in. Scientists wanted a close look at Titan's thick, hazy atmosphere badly enough to trade away everything that would come after it. That single close look bent Voyager 1's trajectory north and pushed it permanently out of the flat plane the planet's orbit in. Once it left that plane, it could never fall back into line for another planetary encounter. Voyager 2, kept close to that same flat plane instead, was free to keep going, onto Uranus, onto Neptune, completing something close to the original Grand Tour almost by itself. One probe finishing a job that was designed for 4. Both probes are still moving. Neither has brakes. Neither is coming back. Voyager 1 climbs north out of the solar system at about 17 kilometers a second, more than 38,000 miles an hour, fast enough to cross the length of the United States in under 5 minutes. Voyager 2 heads south, the opposite direction, carried by the same one-way physics, toward the same fate. There is one more thing worth knowing about that outward journey, something that will matter a great deal later. At one point, NASA completely lost contact with Voyager 2. Completely. Not a weak signal, not a garbled one, nothing at all. And getting it back required a move so extreme, so far past anything the mission had ever attempted, that the people who watched it happen would later call it an interstellar shout. What that shout actually was, and how close it came to failing, is a story for later. For now, both probes are simply outbound, small, fragile, improbably far from home, carrying a message that was never meant to be read by anyone on Earth. 2 spacecraft against the entire outer solar system, launched on borrowed motion, and still listening for instructions from a planet they will never see again. 2.5 years after launch, the first of the twins reached its target. Voyager 1 arrived at Jupiter in early 1979, and for the first time, the faint link stretching back across hundreds of millions of kilometers had something to show for itself. Every previous picture of Jupiter and its moons had come from Earth, filtered through the blur of an atmosphere and the limits of a telescope lens. Decades of careful observation that had still only ever shown fuzzy disks and guesswork. Now there was a camera close enough to actually see, and close enough to be wrong about what it expected to find. Nobody expected much from Io. Jupiter's innermost large moon looked on paper like a plain, dead, cratered rock, the kind of world astronomers had already catalogued 100 times over on other moons circling other planets. Grey, pitted, silent. Something closer to our own moon than to anywhere new. Nobody on the imaging team was looking for anything else. On March 9, 1979, a navigation engineer named Linda Morabito sat processing a routine image of Io, the kind of picture nobody outside Mission Control would ever see. Her job had nothing to do with volcanoes, She was using background stars to check the exact position of the spacecraft. Ordinary bookkeeping, the unglamorous work that keeps a mission pointed the right way. Then, she noticed something at the edge of the moon that should not have been there. A cloud, umbrella-shaped, rising 270 kilometers off the surface. Stack the height of Mount Everest on top of itself, 30 times over, and the cloud would still tower above it. It was not a flaw in the camera. It was not a smudge on the lens. It was the plume of an erupting volcano, later named Pele, caught mid-eruption on a moon nobody was watching for eruptions. Not a plain, dead world. A world tearing itself open from the inside. It marked the first time active volcanism had ever been observed anywhere beyond Earth, on any world, in any image, in the whole history of looking up. And it was found entirely by accident, by someone checking star positions instead of hunting for fire. But here's where it gets strange. Io was not a one-time surprise. It turned out to be the most volcanically active body anywhere in the solar system, more active than Earth itself. Its sulfur plumes shooting more than 500 kilometers into space, a plume tall enough to swallow the cruising altitude of every airplane on Earth, 50 times over. The images came back so extreme that Voyager scientists at first suspected their own instruments, mistaking the plumes for camera errors before slowly accepting what they were actually seeing. How many volcanoes were actually caught erupting at that flyby? The sources still do not agree. 8 plumes in total by one count, 9 currently active volcanoes by another. The exact number is unsettled to this day, and honestly reported as such rather than rounded off to something tidier. What is settled is the cause. Io orbits close enough to Jupiter that the giant planet's gravity flexes the moon's interior over and over, squeezing and stretching it the way a hand kneads dough, and that endless flexing generates enough internal heat to keep sulfur boiling out of the ground, mountain after mountain, year after year. A moon this small was not supposed to have any heat left inside it at all. Jupiter itself supplies the difference, one enormous body quietly cooking a much smaller one through gravity alone. No engine, no radioactive core doing the work, just the relentless pull and release of a planet vastly more massive than the moon it grips. Jupiter had one more surprise waiting that had nothing to do with its moons. In early 1979, Voyager 1 also caught sight of a faint ring circling the planet itself, a ring nobody on Earth had ever detected. Too dim and too thin for any telescope to pick out from this far away. Saturn had its rings, bright and famous and visible in a backyard telescope. Nobody expected Jupiter to have one too, hiding in plain sight the entire time, waiting for a camera close enough and patient enough to notice it. It took a spacecraft hundreds of millions of kilometers from home to see something Earth had been staring past for centuries. The moons kept talking. On Europa, the cameras found long, straight fractures cut across a smooth shell of ice, cracks that looked less like a dead, frozen surface and more like ice that had shifted, split, and healed itself over time. That single detail became among the first evidence that an ocean of liquid water might be sitting beneath that frozen crust, hidden under miles of ice, warmed by the same kind of gravitational flexing already cooking Io next door. And Ganymede turned out to be the largest moon in the entire solar system. Bigger than the planet Mercury, its surface split between 2 distinct kinds of terrain, one heavily cratered and ancient, the other grooved and visibly younger, evidence that the whole icy crust had been pulled, cracked, and reshaped by forces working from within rather than sitting frozen and unchanged since its formation. 2 more moons, 2 more worlds nobody had expected to be interesting, quietly rewriting what a moon was even allowed to be. An ocean sealed under ice, a crust that moves. Neither belonged in the tidy, static picture anyone had drawn of this part of the solar system before Voyager arrived. Every one of these findings followed the same shape. Expect a dead, ordinary world. Find something moving, cracking, or erupting instead. That was the pattern the Jupiter encounter set for the whole mission still ahead. A signal crossing a distance no cable could ever span, delivering pictures no telescope on Earth could gather on its own, and overturning what scientists thought they already knew the moment the pictures arrived. Nobody had planned for a volcanic moon, a hidden ring, and 2 worlds hiding oceans and tectonics under solid ice. Jupiter delivered all 4 before the spacecraft had even left the neighborhood, and every one of those 4 had to travel the same fragile route home, riding a signal too faint to hear without straining for it, across a gap too wide for anything but patience. Jupiter was only the first stop. 2 more giant worlds, and a moon stranger than any seen yet, was still waiting at the far end of the flight. Past Jupiter, the tour only got stranger. At Saturn, the rings that had looked like simple, bright bands from Earth turned out to be built from a finer material than anyone expected. From a backyard telescope, they had always looked flat, smooth, almost drawn on with a compass. Voyager's cameras got close enough to prove otherwise. They caught twists in the rings, kinks that bent the smooth curve out of shape. Thin braided strands wound around each other like rope pulled tight. Small moons orbiting inside the gaps, later named shepherd moons, sculpted the ring edges with their own gravity, herding loose particles the way a sheepdog keeps a flock, pinned inside a fence line. Without them, the rings would slowly spread and blur. With them, the edges stayed sharp, penned in by gravity too faint to see and too precise to ignore. The spacecraft found 5 new moons circling Saturn, and 1 more ring nobody had catalogued before, a faint band now called the G-ring. Rings that had looked painted on from 100 light minutes away turned out to be alive with structure, shepherded, braided, and still shifting under their own gravity. Then came the 2 worlds no probe had ever reached before, and none would reach again for decades. On January 24, 1986, Voyager 2 flew past Uranus. It remains even now the only spacecraft that has ever visited that planet at close range. In under 6 hours, less time than a single workday, it gathered nearly everything humanity still knows about Uranus firsthand. 10 new moons, 2 new rings, and a magnetic field tilted 59 degrees from the planet's own spin axis, unlike any other planet in the solar system. Imagine Earth's magnetic north, sitting not near the Arctic Circle, but tipped more than halfway toward the equator, and that is roughly the arrangement Voyager found circling Uranus. Among the moons it photographed was one called Miranda, a small, battered world that should have looked like any other icy rock. It did not. Its surface was a jumble of canyons, ridges and terrain that simply stopped and restarted at odd angles, as though the moon had been shattered and pieced back together by hand. Scientists nicknamed it the Frankenstein moon, a small world stitched from mismatched parts, patched together from pieces that never should have matched. Nobody expects a moon that small to look that broken. Miranda did anyway. Whoever looks at Uranus next will be building on 6 hours of data gathered nearly 4 decades ago, because no spacecraft has been back since, and none is currently on its way. 3.5 years later, on August 25th, 1989, Voyager 2 reached Neptune, passing within 4,150 kilometers of its cloud tops, closer than a flight from New York to London. It remains, as of 2026, the only spacecraft that has ever visited Neptune. Uranus and Neptune had always been treated as the cold, quiet edge of the planetary map, too far from the sun for much of anything to happen out there. Not cold and quiet, not remotely. Voyager found a storm on Neptune the size of Earth itself, a dark oval capped in high methane ice clouds that scientists named the Great Dark Spot. Unlike Jupiter's Great Red Spot, which has churned for centuries, Neptune's storm turned out to be temporary. It had already dissolved by the time later telescopes went looking for it again, and by tracking bright clouds drifting around that storm frame by frame, Voyager clocked winds exceeding 2,100 kilometers an hour, more than twice as fast as a jet plane at cruising speed, the fastest winds ever recorded on any planet in the solar system. A planet that, far from the sun and that cold, should not have had the energy to drive weather this violent. Neptune did anyway. Gas pushed around faster than anywhere else Voyager had ever measured. Neptune's largest moon had one more surprise waiting. On Triton, Voyager's cameras caught something erupting. Dark plumes of nitrogen gas and icy particles rose about 8 kilometers into the thin sky, about as high as a passenger jet cruiser's, then streamed downwind for more than 100 kilometers, about as far as a car covers in an hour on the open highway. before settling back down as dark streaks across the ice. Triton's surface measured about 38 degrees above absolute zero, close to minus 235 degrees Celsius, colder than liquid nitrogen, cold enough to freeze nitrogen gas itself, solid on the ground. A world that cold, that far from the sun, should have gone still long ago, every process frozen along with the ground, and yet something beneath that frozen crust was still active enough to punch geysers straight through it. Scientists still do not agree on exactly what drives them. Sunlight warming a hidden layer of nitrogen ice is the leading idea, but it remains unconfirmed. What is not in question is the shape of the surprise. The outer solar system's last stop turned out to be one of its most active worlds, not its quietest. 2 planets no craft has visited since. A moon nobody expected to be alive. Every image, every measurement still stands today as the primary record humanity has of that entire stretch of the solar system, because nothing has gone back to check. Then, on February 14, 1990, Voyager 1 did something it had never been asked to do before. From nearly 6 billion kilometers away, roughly 3.7 billion miles, so far that its own light took more than 5 hours to reach home, the spacecraft turned its camera back toward the inner solar system and took 60 images, a single portrait of the whole family of planets it had left behind. In one of those frames, Earth appeared as a single point of light, a crescent covering barely 1/10 of 1 pixel, less than a dot in the frame. Astronomer Carl Sagan had pushed for that image for years. Wait, most of the Voyager team did not want to take it. Pointing the camera back toward the sun risked damaging the optics, and the engineering effort was already stretched thin, keeping both probes alive at the edge of their design life. Sagan insisted anyway. The picture was taken on the mission's last practical chance before the cameras were switched off for good, to save what little power the spacecraft had left to give. Everything this section has described, the braided rings, the tilted field, the shattered-looking moon, the fastest winds ever clocked on any planet, the geysers punching through frozen nitrogen, all of it happened on worlds far larger than the one holding the camera. And in the end, the most lasting image of the entire flight was not of any of them. It was a single frame, taken looking backward, holding an entire planet and everyone who had ever lived on it, in less than a dot of light. The cameras had done their work. Whatever came next, it would not be through a lens. The cameras were finished, but neither probe was empty. Each one still carried something that had never needed a lens at all, bolted to the outside of the spacecraft, where any eye that ever found it could not miss it. A disc of gold-plated copper, 12 inches across, the same width as an ordinary vinyl record sitting on a shelf at home. Assembling what would ride on that disc fell to a small committee chaired by the astronomer Carl Sagan of Cornell. Around him worked creative director Ann Druyan, astronomer Frank Drake, writer Timothy Ferris, artist John Lomberg, Linda Solzman, and 2 ethnomusicologists, scholars of music across world cultures, Robert Brown and Alan Lomax. Their assignment was absurd on its face. Compress everything a stranger might need to know about Earth onto one disk, with only months to do it, before the launch dates already locked in for both spacecraft. There was no time to deliberate for years over what humanity should say about itself. There was barely time to agree at all. A message in a bottle usually gets 1 sentence and a name. This one had to be a whole civilization, chosen fast by a handful of people. And it had to be right, because there would be no second disc and no way to update the first once it left the ground. They opened with language. 55 spoken greetings, recorded in 55 different tongues, starting with Akkadian, a language spoken in Sumer some 6,000 years ago, and closing with Wu, a dialect still spoken in China today. Somewhere in that chain, Sagan let his own young son, Nick, say hello. One voice from one household folded in among 54 others, spanning most of recorded human history. Onto the same disc, pressed as analog signal, the same continuous method used to cut an ordinary vinyl record. They encoded 115 images, or 116 depending on which account you read, one of them a plain calibration circle rather than a photograph. The rest, chosen to stand in for the whole of ordinary Earth, for an audience that had never seen it. They added 90 minutes of music chosen for how little of the planet it left out. Bach, Beethoven, Mozart, Stravinsky, Chuck Berry's Johnny B. Good, Blind Willie Johnson, Louis Armstrong, Indian classical ragas, panpipes from the Andes, and they layered in 12 minutes they called Sounds of Earth, surf breaking, wind, thunder, animal calls, birdsong, the ordinary noise of people going about a day. Here is something none of the liner notes mention. Hidden inside that 12-minute montage is an hour of one woman's brainwaves and heartbeat, recorded and compressed down to about a minute, folded in among the wind and the surf, where a casual listener would never pick it out. The woman was Anne Druyan. The recording was made only days after she and Sagan had agreed, over the phone, to marry. Her thoughts drifted across those minutes from the long sweep of human history towards something much smaller and much closer, what it felt like, right then, to fall in love. Not a sound effect, a heartbeat, a real one, riding past the edge of the solar system, hidden in plain hearing. The disk carrying that pulse looks, at a glance, like nothing special. 12 inches of gold-plated copper, sealed inside an aluminum jacket with a cartridge and a needle packed alongside it. No player was included. Whoever finds it will have to build their own. So the cover does the explaining. Etched into the aluminum is a diagram of the disc and the stylus, marked with the correct starting point, and instructions to play it from the outside edge inward, at 16 2/3 revolutions a minute. Exactly half the speed of an ordinary household record, which spins at 33 1/3. The rotation period itself is spelled out in binary, timed not in seconds or minutes, but in the flicker of a hydrogen atom switching states. A unit that means the same thing anywhere in the universe, unlike a clock built for one planet. The cover carries one more set of instructions. 14 lines radiate outward from a single point, each one aimed at a pulsar, a collapsed fast-spinning star that sweeps a beam of radiation past Earth on a rhythm as steady as a lighthouse, each line labeled in binary with that pulsar's own rotation period. Line the real sky up against that pattern and, in theory, a finder could work backward to the sun itself, and to roughly when the record left it. As a second check, the cover holds an actual sample of uranium-238, plated directly onto the metal. Uranium decays on a clock of its own, a half-life, the span it takes for half of any sample to break down, of about 4.5 billion years, close to the age of Earth itself. Measuring how much it decayed would tell a finder how long the record had been drifting, cross-checked against the pulsar pattern. It looks like a piece of 1970s hardware, built the way a living room record was built that decade. Gold plating instead of vinyl, an aluminum sleeve instead of a paper jacket. Not disposable technology. A time capsule built on purpose to survive its makers. Every language recorded on that disc will eventually stop being spoken. The people who chose the music will not outlive it. Even the world it was built to describe may not outlive it. The record was engineered to keep working long after all of that is gone. Two decisions from that committee still surface in the record's story. NASA had already taken criticism over an earlier probe, Pioneer, for engraving a nude man and woman onto its own plaque, and this time the agency blocked a planned photograph of a nude man and a pregnant woman outright. The team replaced it with a plain black silhouette of the same two figures. The shapes kept, the image itself withheld, and nobody fully agrees on how Johnny B. Good made the final cut. One account has Alan Lomax objecting that rock and roll was music for adolescents, and Sagan overruling him on the spot. There are a lot of adolescents on the planet. Another account credits a young Bill Nye with pushing for the song instead. Both versions survive. Neither has ever been settled. Nobody knows how long the record will actually last. Estimates run from a few million years to a billion or more, some pushing further still, since almost nothing erodes it out in the vacuum between stars. Nobody knows if it will ever be found either. Voyager 1 is not due to pass within roughly 1.6 light-years of another star, one called Gliese 445, for about 40,000 years, and even then, whether anyone could decode a diagram etched in aluminum has never been tested by so much as one confirmed reader. For now, the record travels in silence, doing nothing, carrying everything, waiting for a listener that may never arrive, on a schedule measured in billions of years rather than in one human lifetime. The signal is different. The signal is still working right now, every single day, and reaching it took building some of the most sensitive machinery human beings have ever pointed at the sky. For any of that to reach us, though, someone has to be listening, and listening turns out to be almost impossible. Each Voyager beams its signal home through a dish 3.7 meters across, about the width of a small backyard patio, aimed by a transmitter that draws only about 20 to 23 watts. That is roughly the power of the bulb inside a refrigerator door. The transmission goes out on two separate frequency bands, called S-band and X-band, the higher one running near 8 billion cycles a second. But the wattage behind either one stays the same, a bulb's worth of power. It just screams as loud as it can across more than 24 billion kilometers, and hopes someone is listening on the other end. A fridge light, aimed at nothing, crossing a gap that size. Someone is. NASA built the Deep Space Network to do nothing else. 3 antenna complexes, one near Barstow, California, called Goldstone, one outside Madrid, and one outside Canberra, Australia. Each complex is built around a dish 70 meters wide as a football field is long, backed up by a 26-meter dish, and several more at 34 meters. The placement is not an accident. Earth turns, and any single antenna eventually rotates its own dish away from the sky it was pointed at. So, the 3 sit about 120 degrees apart in longitude, 1/3 of the way around the globe from each other. Spaced so that before a spacecraft sinks below the horizon at one site, the next is already climbing into view at another. Once a mission is more than about 30,000 kilometers out, less than one trip around Earth's own equator, at least one of the 3 can always see it. Contact never has to end. The network was built so the planet's own rotation could never be the reason Voyager fell silent. Here is what that contact is actually catching. By the time Voyager's transmission reaches a dish, it is thinned to somewhere between a 10 quadrillionth of a watt and less than a billionth of a watt. Sources disagree on exactly which, and the honest answer is both figures get used, depending on how the measurement is taken. NASA offers its own comparison. A digital watch on your wrist runs at a power level about 20 billion times greater than the whisper striking that dish. Think about what that means for the dish itself. The largest reflector on the whole network exists for the sole purpose of catching something weaker than the battery in a $5 watch. Not overkill, the minimum required. But the reality was different. To send a command out to Voyager, the same network blasts with tens of thousands of watts, enough to run thousands of homes. To hear Voyager answer, it has to catch something 20 billion times weaker than a watch battery. Not a faint signal. A signal at the ragged edge of existing at all. Shouting is easy when the shouter has an entire planet's power grid behind it. Whispering back across the same distance, with only its own shrinking onboard power to draw on, is the harder trick, and it is Voyager's alone to perform. Catching it takes more than a big dish. Bolted behind each antenna sits a receiver called a masser, cooled with liquid helium down to about 4 degrees above absolute zero, a temperature colder than anything found naturally anywhere on Earth. Even a receiver's own heat generates enough thermal static to drown a signal this weak, so the colder the bath, the better the mesa hears. Warm the receiver by even a few degrees, and the whisper disappears into its own static. The whole apparatus exists to chill down the machine, just to let one whisper through. None of it runs itself. Every mesa, every dish bearing, every cooling line is tended by people, and the fridge bulb signal only survives the trip because someone on the ground keeps the receiving end that carefully maintained. And even that is no longer quite enough. Voyager is now so far out that a single dish cannot pull in everything it sends. The network electronically links several antennas together, arraying them so they listen as one larger ear, stitching their signals into something stronger than any one of them alone. A 5-antenna array is already required just to recover data from Voyager 1's plasma wave instrument, and NASA expects it will need 6 before much longer. On April 20th, 2024, engineers linked all 6 radio antennas at the Madrid complex together for the first time, combining them to receive Voyager 1. The wavefront does not strike every dish at once. It reaches each one a fraction of a second apart, so software has to correct for that lag and for shifting atmospheric conditions in real time, or the combined signal cancels itself out instead of strengthening. The network doing all this is not indestructible. On September 16th, 2025, the 70-meter dish at Goldstone, the one called DSS-14, was tracking the Juno spacecraft at Jupiter when a control system misreported its position and let the dish over-rotate. Safeguards that should have stopped it did not. Damaged fire suppression lines let roughly 200,000 gallons flood the dish's base, almost 2 years' worth of water for an average household, gone in an afternoon. Repairs are estimated at $4 to $4.5 million, with the dish not expected back in service until around October 2028. Not a glitch. A dish this network needs, gone for years, at the exact moment it needs every dish it has. Separately, in late July 2026, a wildfire burned through the hills around the Madrid complex, the very site that had just linked all 6 of its antennas to keep hearing Voyager 1 at all. As of this telling, whether the antennas came through unharmed still is not confirmed. A network built to survive Earth's rotation, its own aging hardware, even fire, just to keep one 20-watt bulb of a signal from going unheard. None of that is the end of the difficulty either. Catching the whisper across 24 billion kilometers is only the first problem. What arrives at the massa is not a clean message sitting ready to read. It is a signal buried in drift, stretched and squeezed by the motion of 2 bodies that never sit still relative to each other. And reading it turns out to be a fight of its own. Say the dish does hold the whisper, and the massa keeps it from drowning in its own static. The message still is not sitting there ready to read. It arrives late, it arrives shifted, and neither problem announces itself before it strikes. Start with how late. Sunlight takes about 8 minutes to cross from the sun to Earth. That number barely changes year to year, because Earth's distance from the sun barely changes. Voyager 1 offers no such comfort. Its signal, as of December 2025, takes about 23 hours and 32 minutes to make that same one-way trip, and the gap keeps widening every single day, because the spacecraft keeps moving and never comes back. On about November 18, 2026, that light time is set to cross a full 24 hours, one entire light day, at a distance near 25.9 billion kilometers. No object built by human hands has ever reached that milestone before. Right now, Voyager 1 sits roughly 25.5 to 25.8 billion kilometers out, about 172.6 astronomical units, some 16 billion miles, a distance that keeps the whole story anchored to the same 24 billion kilometer scale it opened on. The number will keep climbing. It has never once gone down. That lag rewrites what a command even means. Send one up, and the answer does not come back the same afternoon. It does not come back the next morning either. NASA's own project manager, Susie Dodd, put it plainly. Send a command Monday morning, and its effect shows up Wednesday morning. Every instruction to Voyager is a 2-day round trip before anyone on the ground knows whether it worked. A decision made and then set aside, unconfirmed, for a span longer than most people take to plan a weekend. And the delay is only the first complication. Voyager 1 is pulling away at about 17 kilometers a second. Voyager 2, on its own path, trails a little behind at close to 15.4 kilometers a second. Earth is not standing still either. It swings around the sun at nearly 30 kilometers a second, faster than either probe is receding, almost twice Voyager 2's own outward crawl. So for part of every year, Earth's own motion closes the gap, quicker than the spacecraft opens it. And the distance between Earth and Voyager, and the signal's own pitch, briefly shrinks before it climbs again. 2 bodies, never at a fixed distance, never at a fixed relative speed, exchanging a signal that has to survive both. That constant change in relative speed drags the signal's frequency along with it. It is the same effect that reddens the light of a galaxy racing away, stretched by motion into a different wavelength than it left with. At Voyager's X-band frequency, every kilometer a second of relative speed shifts the signal by about 28 kilohertz, and across the whole mission that shift has swung by roughly plus or minus 30 kilohertz as Earth turns and both bodies move. Voyager's own downlink is generated near 8,420.43 megahertz, held steady to under 1 cycle in 8 billion at the spacecraft itself. precise enough that a drift of only a few kilohertz is not noise. It is the whole signal sliding out from under wherever a receiver expects to find it. That is when the pattern broke. A shift that size, at a distance that large, should mean the signal keeps drifting out of whatever narrow window a receiver is listening in, the way a radio station slips out of tune as a car drives further from the tower. It does not. Not because the drift stops, because the deep space network never waits to react to it. Ground stations calculate the coming shift in advance, straight from the same orbital tracking data that already tells them exactly where Voyager is and how fast it is moving relative to the dish, and retune both the outgoing frequency and the receiver's own search window to meet the signal exactly where it will be, minutes or hours before it arrives, not chasing the drift, arriving there first. Even caught and steady, what comes down the line is thin. Voyager now sends data at 160 bits a second under normal operations, rising only to 1.4 kilobits a second when it replays stored plasma wave recordings, a rate that has not changed since interstellar space began. Slower than the weakest dial-up modem ever sold. Slower than a page of text typed out one character at a time. At a trickle that thin, every bit has to count, which means every bit has to be protected, because a single flip digit lost in transit cannot simply be asked for again, not with a 2-day wait between the asking and the answer. That protection has been rewritten in flight, twice, without anyone touching the transmitter. From 1977 through roughly the Uranus flyby, Voyager's telemetry ran through a concatenated scheme, an inner convolutional code paired with an outer Golay code, both of them just structured ways of padding a message with extra, predictable bits so a receiver can spot and fix a corrupted one without asking Voyager to resend it. That protection cost nearly as much overhead as the data itself, close to a full extra copy riding along with every message. Ahead of Uranus and Neptune, engineers on the ground wrote new flight software and uplinked it across that same fading link, swapping in a Reed-Solomon outer code that cut the overhead to about a fifth of the message, instead of the whole thing again. The error rate dropped at the same time, from roughly one bad bit in every 20,000 down to about 1 in a million. Not a hardware fix. A rewrite sent from Earth, installed on a computer already billions of kilometers gone, doing better work than the version it replaced. None of it touched the antenna, the dish, or the 20-watt whisper leaving the spacecraft. Every gain came from smarter listening and smarter code, squeezed out of a link that was never going to get any stronger on its own. Distance could not be shortened, power could not be raised, so the only variable left to improve was the intelligence applied to the signal at both ends, and for nearly 5 decades that has been enough. Catching the whisper and reading it cleanly, that took decades of patient engineering from this end alone. Getting a message the other way, into Voyager's own ear, was about to prove a stranger kind of problem still. Hearing the whisper turned out to be one problem. Making Voyager hear anything back is the opposite one, and it is stranger still. The same 70-meter dishes that spent the last stretch straining for an Atawatt turn out to be more than capable of shouting. On the way up, the Deep Space Network's transmitters push commands out at around 20 kilowatts. Enough electricity to run several dozen homes at once, all of it aimed in a tight beam at a single point crawling across the sky. At Canberra, the dish designated DSS-43 carries something stronger still, an optional 400 kilowatt S-band amplifier, roughly the draw of a small neighborhood, held in reserve for whenever a fainter shout will not reach. Nothing about sending a command is delicate. It is closer to brute force, aimed with extreme precision. Against Voyager's own reply, a signal that never rises past 23 watts. That gap is enormous. Something like 900 times more power leaving Earth than ever comes back from the spacecraft. And at Canberra's full strength, closer to 20,000 times. The simplest way to say it is the source's own way. What Earth sends up to Voyager is over 1,000 times stronger than the whisper Earth receives in return. Turn that around, and it reads just as strangely from the other side. Voyager's whole reply carries at best 1,000th of the strength Earth used to ask the question. 2 directions on the same link, carrying 2 completely different budgets. The reason is not cleverness, it is budget. Earth can pour as much electricity into a transmitter as it wants, drawn from an entire planet's power grid, so it shouts because it can afford to. Voyager cannot. Every watt aboard the spacecraft comes from a nuclear generator that has been quietly losing strength for close to 50 years, a shrinking allowance the mission has had to ration since before it left the solar system. A story the power system itself will tell in full later. Earth affords volume, Voyager affords almost nothing, and what little it has keeps shrinking. So Earth shouts, and Voyager, by comparison, barely whispers back. It is the same imbalance the whole mission runs on, a fridge bulb transmitter answering a planet's own power grid, small against scale in exactly the way this link has always been. There is no fixing that gap from Voyager's end. No larger transmitter is coming. No new fuel is on the way. The only lever left is Earth's own patience and Earth's own power, applied over and over, decade after decade, so that the conversation can continue even though only one side of it can ever afford to raise its voice. But the power gap is not the strangest part of this exchange. The strangest part is what Voyager does with the signal once it lands. How does a spacecraft that cannot spare the power to shout also manage to hold a steady, precise frequency across 24 billion kilometers? It does not. That is the answer. Voyager's onboard clock, the oscillator that would normally set its own broadcast frequency, is not steady enough to be trusted on its own. Left to run by itself, it would drift. And a drifting frequency is exactly the kind of problem the ground stations already fight hard enough to solve from their end. So the spacecraft does not try to solve it twice. Its transponder, the same electronics that handle both directions of the link, locks onto whatever frequency arrives from Earth and multiplies it by a fixed ratio, then sends that product back down as its own reply. One consequence of that arrangement is genuinely elegant. Because the returning signal is mathematically tied to the one sent up, a single round trip captures the Doppler shift in both directions at once, the same shift the ground stations spend their days predicting and meeting, before it ever has the chance to drift out from under them. Send one signal up, and the number that comes back down already carries the answer to a question about both directions of travel at once. Engineers did not have to build two separate systems to measure two separate shifts. One coherent link did the work of two. The other consequence is stranger. Voyager does not answer Earth in a voice of its own. It hears Earth's carrier, and it sings that same carrier back, multiplied. Not an independent transmission, built from the spacecraft's own timing and sent out on its own authority. An echo, caught, amplified, and returned. Every reply Voyager has ever sent home carries Earth's own pitch inside it. The exact frequency used to command Voyager 2 is 2113,325 megahertz, an oddly specific number for what looks like a small technical detail buried inside a much bigger system. Engineers built the transponder around that one narrow value and moved on to other problems, confident it would simply keep working quietly for as long as the mission lasted. It will matter again later, in a way nobody designing that transponder decades ago could have expected. For now, it is enough to know the shape of the exchange. Earth shouts with the strength of a power grid. Voyager answers with a whisper it cannot even generate on its own, only catch and reflect back, note for note. That dependency made the precise tracking of a spacecraft billions of kilometers out possible, elegant enough that engineers built the whole tracking system around it. It was also, quietly, a vulnerability. A spacecraft that only speaks by echoing what it hears is a spacecraft that goes silent the moment it stops hearing anything at all, and that single fact would eventually come within reach of costing the mission everything. That single dependency lived inside the radio. The brain behind it is smaller still. Each Voyager carries 3 computer subsystems, and each of those is built in pairs, one working, one standing by, 6 machines in total. The computer command system reads incoming instructions and watches for trouble, the closest thing the spacecraft has to a decision maker. The flight data system packages science and engineering readings into a form the radio can actually send. The attitude and articulation control system keeps the craft steady and its dish aimed at a planet it can no longer see with anything but instruments, holding that aim across 4.5 decades without a hand to correct it. Combined, all 6 hold about 68 kilobytes of memory. That is less than the chip inside a car key sitting in someone's pocket right now. 68 kilobytes is a strange number to hold an interstellar mission together. It is smaller than a single photo taken on a modern phone and compressed for a text message. The physical package housing the data formatting computer is roughly the size of a loaf of bread, and inside that loaf sits the memory now carrying every image, every reading, every package transmission the mission still sends home. Not all of that memory survives the same way. The command system and the pointing system store their instructions on plated wire, magnetic patterns burned into iron-nickel strands, data that stays put even if every scrap of power vanished tonight. The data formatting system works differently. It's memory built from chips that forget everything the instant power drops. So engineers wired that memory straight to the nuclear generators, past the main power line entirely, so that only the total death of all 3 generators could ever erase it. By then, nothing else about the mission would matter either. Speed tells the same story. The whole spacecraft, all 6 computers working together, processes about 8,000 instructions a second, a 4 megahertz master clock, driving a processor that runs at a quarter of that, each instruction taking roughly 80 millionths of a second to complete. A smartphone in a coat pocket runs more than 14 billion instructions in that same second. Voyager's entire mind moves roughly 1.75 million times slower than the phone taking that comparison's own photograph. A machine that's small, that's slow, running code written before most of the people who now operate it were born, should be a fossil, something you leave alone and hope keeps ticking. But here's where it gets strange. On November 14, 2023, Voyager 1 started sending home nonsense. Strings of unreadable data even though it was still receiving commands and carrying them out correctly. It was listening. It just could not speak clearly anymore. A team at JPL built out a dependency chart of every system on the spacecraft, tracing what fed into what, working across the same nearly 2-day round trip. Every command and every answer had to survive. By March of 2024, they had narrowed the fault to 1 failed memory chip inside the data formatting system. A chip holding just 256 words, corrupted just enough to scramble part of the code that packages every reading before it goes out. The likely cause was never nailed down for certain ordinary age or a single cosmic ray strike, either one plausible on hardware that has now spent nearly 50 years outside any atmosphere thick enough to shield it. There was no free block of memory large enough to hold that code in one piece anywhere else on the machine. So the team split it. They broke the affected code into fragments, tucked each fragment into whatever scattered free space the aging memory still had, rewrote each piece so it would run correctly from its new address, and updated every other line of code that had ever pointed toward the old one. Every reference, everywhere, rewritten to find the code in its new scattered home. The fix went up on April 18, 2024. It was confirmed working 2 days later. Nobody ever touched the broken chip itself. They worked around it entirely, across a gap wide enough that every command took most of a day just to arrive. Not routine maintenance. A live surgery performed at a distance no surgeon has ever operated across, on a patient that cannot be paused. Every step of that surgery had to be checked, sent, and confirmed across the same lag the whole mission now runs on. A single wrong address, one reference left pointing at the old location, could have meant losing the data formatting system entirely, and with it the ability to send anything meaningful home at all. There was no room to guess, and the tools available for that surgery were nothing like what a modern engineer would expect. The flight software runs in assembly language, written for custom processors General Electric, built in the early 1970s, a language few people still learn and fewer still practice on hardware this old. When Voyager launched, engineers had a dedicated testbed, a ground copy of the flight computer built specifically for writing and safely checking new code before it ever reached the real spacecraft. That testbed is gone, decommissioned decades ago, because nobody building it imagined the mission would outlive it. Every recent fix has been written and sent without that safety net, and the team has spent recent years rebuilding a simulator from scratch. essentially reconstructing the workshop after deciding the tool inside it still has work left to do. This was not the first time old code was trusted with the mission's survival. On November 28, 2017, engineers fired 4 backup trajectory thrusters on Voyager 1 that had not been used since 1980, 37 years dormant, in pulses just 10 milliseconds long. Before they dared it, they dug up the decades-old assembler code, checked it line by line, and confirmed it would still do exactly what it once did. It worked. The maneuver bought the mission an estimated 2 to 3 more years of pointing accuracy, pulled out of a drawer that had not been opened since Disco was still on the radio, who was still fluent enough in a 1970s assembly language to write and trust code like this. That question does not have a clean answer yet. Only an old, often repeated claim about a handful of engineers well into their 80s, a figure that traces back to reporting from years ago and should not be taken as current. Whoever they are now, they are the ones this entire chapter runs through. 68 kilobytes, 6 computers, a language almost nobody writes anymore, and still, every so often, a small patient repair reaches across 24 billion kilometers and lands exactly where it was aimed. The power running all of it, though, was never going to last forever, and that decline had already been written into the mission from the day it launched. Every fix so far has come with an undo. This one does not. Both probes carry 3 power sources called radioisotope thermoelectric generators, RTGs for short, sealed units with no moving parts and nothing inside to repair. Bolted to each craft since before launch, the 3 RTGs together produced about 470 watts of electricity in 1977, roughly the running draw of a handful of household light bulbs wired together. That number was the ceiling on day 1. It has only gone down since. An RTG makes power through something called the Seebeck effect. Join 2 different metals in a loop, heat one junction and cool the other, and the temperature gap alone pushes electrons across. No fuel burns. Nothing spins. It is the same basic principle behind a small thermoelectric charger sold for camping trips. The kind you clip to the side of a stove so a pot of boiling water can trickle a little electricity into a phone. Voyager runs on that same idea, except the heat never comes from a flame someone lit and can put out. It comes from a plutonium quietly falling apart, and it will keep coming whether anyone wants it to or not. Inside each generator, a lump of decaying plutonium-238 heats one side past 1,000 degrees Fahrenheit, hot enough to glow, hot enough to melt lead outright, while the other side radiates its heat into the cold of open space. That gap between hot and cold is the whole engine. A nuclear battery, built once, sealed shut, never refueled, never touched again. Plutonium-238 decays on a fixed schedule. Its half-life is 87.7 years, long enough that the fuel will outlast the engineers who built it, and most of the ones flying it today. Each generator carries about 4.5 kilograms of the stuff, a little heavier than a bowling ball, producing roughly 1700 watts of heat across all 3 generators on a single craft. Only about 470 of those watts ever became usable electricity. The rest simply radiated away, unused, an efficiency under 7% by design, and that was the good year. Here is where the story gets less clean. Physics alone should have made the decline predictable, one smooth curve traced from the half-life and nothing else. By the year 2000, 23 years after launch, that curve predicted the generator should still deliver 83.4% of their launch output. The real figure was only about 67%, not a rounding error, not a measurement mistake, 16 points below what decay alone could explain. Something else had been aging too. A second clock had been running the whole time. The thermocouples, the actual metal junctions doing the converting, wear down on their own the longer they sit at those extreme temperatures, completely apart from how much plutonium is left to decay. 2 failures stacked on top of each other, one nuclear, one mechanical, both irreversible. By early 2001, Voyager 1 sat at about 315 watts, Voyager 2 at about 319. Neither has climbed since. The fall has kept going at a steady pace, close to 4 watts lost every year on each craft. A loss so small, it would barely run a nightlight, and yet it never stops, never pauses, never resets. Different reports place the current total slightly differently, something near 220 watts a few years back, drifting down toward the 230 to 250 range in the most recent figures depending on exactly when the measurement was taken. The transmitter alone eats roughly 200 watts of whatever remains just to run its own hardware, before a single instrument gets a share. That is what it costs to keep the equipment running, not the whisper of power it actually radiates outward across the dark. So something has to give every year. Each Voyager launched with 10 sets of science instruments. 7 are gone now. The photopolarimeter failed first, back in 1980 and 1981. The cameras went dark in February 1990 after the pale blue dot photograph. The infrared spectrometer followed in June 1998. The plasma spectrometer, already dead since 1980, was formally switched off in 2007. Planetary radio astronomy went in 2008. The ultraviolet spectrometer in April 2016. The cosmic ray subsystem in February 2025. And the low-energy charged particle instrument went quiet in April 2026. Though engineers deliberately left a tiny half-watt motor inside it still turning, just in case there is ever a reason to try waking it again. As of April 2026, Voyager 1 has 2 instruments still listening, the magnetometer and the plasma wave subsystem. Voyager 2 has kept slightly more, roughly 3, after switching off its own plasma science instrument in September 2024. A single command that took 19 hours just to arrive, and its charged particle instrument the following spring. None of that order was improvised in the moment. The teams flying these 2 probes settled the shutdown sequence years in advance, weighing which instruments still had something unique left to say against how much power the mission could spare, one careful trade at a time. There is one more move left to try. NASA calls it, informally, the Big Bang Plan, rewiring each spacecraft to swap power-hungry components for leaner ones, freeing up just enough margin to keep one more instrument breathing into the 2030s, maybe even coax a retired one back on. It is not a new source of power. There is no such thing available out there. It is only a way to spend the same shrinking supply more carefully, squeezing a few more years out of watts that were already accounted for. Testing is scheduled on Voyager 2 for May and June of 2026, and on Voyager 1 no sooner than July. Even if it works, 2 different floors are quoted for how long any of this actually buys. Engineering telemetry, the basic pulse confirming the spacecraft is still alive, might continue to about 2036. The last working science instrument is expected to fall silent before that, sometime in the 2030s, and nobody will name the exact year yet. Every rescue this mission has pulled off so far, the rewritten code, the resurrected thrusters, the retuned frequencies, worked because something broken could be worked around. The power is different. Nothing gets patched. Nothing gets rerouted from a backup. It only runs down a little further every year on a schedule fixed the moment the plutonium was sealed into 3 canisters back in 1977. That much was already decided before either probe ever left the ground. What it could not decide was how far the 2 of them would get, and what they would find out there, before the lights went out one by one. What was not decided, back in 1977, is where the signal itself would eventually be coming from. By 2026, both probes are transmitting from somewhere no earlier piece of human equipment had ever reached. Not deep space in the ordinary sense, genuinely between the stars. The sun does not simply sit in a fixed sky and shine, it blows. A constant outward wind of charged particles streams off it in every direction, dragging the sun's own magnetic field along with it, and together they inflate a vast bubble around the whole solar system called the heliosphere. Inside that bubble, the sun is in charge. Its wind pushes back everything trying to press in from the space between stars. The heliosphere behaves less like a fixed shell and more like a ship sailing through the interstellar medium, pushing a wake out ahead of it and trailing a long tail behind, which is why its outer edge is not a tidy sphere. That outer edge has a name, the heliopause, the place where the sun's wind finally loses the argument, and interstellar space takes over. It is not fixed either. It moves in and out with the sun's own activity, expanding and contracting like a lung. Well before that edge sits an inner boundary called the termination shock, where the solar wind, moving faster than sound for the entire trip out from the sun, abruptly slows to a crawl. Voyager 1 crossed the termination shock first, in December 2004, at 94 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, so 94 of them laid end to end. Voyager 2 crossed its own termination shock in August 2007, only 84 astronomical units out, closer in than its twin. The heliosphere is not a perfect ball. It is dented and dragged, thinner on one side than the other, so where a probe crosses its edge depends on which direction it happens to be traveling. The real prize sat farther out still. On July 28, 2012, Voyager 1's instruments started behaving strangely. The rate of galactic cosmic rays reaching the spacecraft jumped. The number of particles streaming from the sun itself plummeted. The surrounding magnetic field roughly doubled in strength, from about 0.2 to about 0.4 nanotesla. Over the next month, the boundary blurred back and forth across the spacecraft 5 separate times, in and out, before one final crossing held. On August 25, 2012, at roughly 121 astronomical units out, something like 11 to 12 billion miles from the sun, Voyager 1 crossed the heliopause for good, and became the first human-made object ever to leave the sun's bubble entirely. A boundary like that sounds like it should announce itself instantly. An unmistakable line crossed once, and confirmed on the spot. It did not work that way at all. The one instrument built to measure the surrounding plasma directly, the plasma science instrument, and settle the question outright, had already been dead for more than 3 decades. It failed back in 1980, long before anyone even knew there would be a boundary this far out worth measuring. The magnetometer alone could show that the field had changed. It could not prove what kind of space the probe was actually sitting in. Proof came later, and sideways. On April 9, 2013, a burst of activity from the sun finally reached Voyager 1, and set the plasma around it ringing, almost like a bell struck once and left to hum. The plasma wave instrument, a separate system, still working, picked up that ring as an oscillation near 2.6 kHz. From the pitch of that oscillation, scientists worked out the density of electrons in the surrounding space, about 0.08 per cubic centimeter, dozens of empty cubic centimeters between each stray electron. Solar wind plasma, thin as it already is, holds roughly 0.002 electrons per cubic centimeter. Interstellar plasma runs about 50 times denser, closer to 0.1. The reading matched interstellar space, not the sun's own wind, and that single measurement, arriving nearly 8 months after the crossing it confirmed, is what finally settled the argument. Not every prediction held up as cleanly. One leading model had expected the interstellar magnetic field to point in a sharply different direction from the sun's own field, so that leaving the heliosphere should have swung it dramatically. Instead, the field barely changed direction at all. Only its strength shifted. That mismatch is a large part of why so many scientists hesitated to accept the 2012 crossing for the better part of a year, and it still is not fully explained. Voyager 2 had an easier time of it. Its own plasma instrument was still alive when it crossed on November 5, 2018, about 11 billion miles out, near the heliosphere's southern flank rather than the nose Voyager 1 had gone through, and at a different point in the sun's own activity cycle. So the confirmation was immediate, not indirect. It also found something worth noting on the way through: plasma running between 30,000 and 50,000 Kelvin, hotter than the surface of the sun itself, evidence of interstellar material compressed and heated, right where it presses against the heliosphere's outer wall. Voyager 1 kept listening. In 2021, scientists reported that its plasma wave instrument had been picking up a faint, continuous hum from the interstellar medium since 2017. A sound with nobody speaking it, just space itself, quietly measurable for the first time by anything humans had ever built. By 2023, that steady listening put the density near the spacecraft at about 0.147 electrons per cubic centimeter, the clearest reading yet of what lies just outside the sun's reach. None of this means either probe has left the solar system, not in the way gravity defines it. The sun's pull, and the icy debris still orbiting far out under that pull, extend well past the heliopause. NASA's own estimate puts Voyager 1 about 300 years away from even reaching the inner edge of the Oort cloud, the shell of icy bodies that marks the sun's true gravitational reach, and something closer to 30,000 years from passing all the way through it, longer than the whole of recorded human history repeated several times over. The edge of the sun's wind and the edge of the sun's grip are not the same line at all. Two probes then, transmitting from a region no signal had ever come from before, still bound, however loosely, to the star that built them. What almost cut that signal off entirely had nothing to do with distance at all. It happened in April 1978, 8 months into the flight, when nothing was supposed to go wrong yet, and nothing looked like it had gone wrong. Voyager 2 was still deep in cruise, years from Jupiter, running on a receiver and a backup that had both performed exactly as designed since the pad. There was no reason yet to expect either one to matter more than routine hardware ever does. On board Voyager 2, a 7-day events timer was counting down, watching for a routine command to arrive from Earth before it reached 0. This was not unusual. The spacecraft carried the timer as a safeguard, a way of noticing on its own if the link to Earth ever went quiet for too long. That week, no command came, for reasons nobody on the ground had planned. The timer reached 0 anyway. The spacecraft's own fault protection software read the silence as failure, not a missed schedule, a broken receiver. So it did exactly what it had been built to do. It switched itself over to the backup receiver, a piece of hardware that had sat unused since launch, carried along for precisely this kind of moment, and never once called on until now. The switch itself worked perfectly. The problem was what it switched to. Nobody on the ground had any way of knowing what was waiting inside that backup. A single capacitor in its tracking loop had shorted. Nobody would ever pin down exactly when. That capacitor's one job was to let the receiver's lock frequency drift automatically, following the same small Doppler shift that Earth and the spacecraft impose on every signal passing between them. Shorted, it could no longer drift with anything. The backup could hear one frequency, and only one, out of all the frequencies a receiver like this was designed to search. Controllers did not know that yet. Weeks later, once the spacecraft appeared stable again, they tried the obvious fix, switching Voyager 2 back to its primary receiver, the one that had never actually failed in the first place. During that switch, an electrical short blew both of the primary's fuses at once. It died instantly. It died for good. The receiver that had worked perfectly through launch, through cruise, through 8 months of flawless service, was gone in the same command that was meant to restore it. The fault logic did not fall back to the backup right away either. For about a week, Voyager 2 sat completely out of contact, deaf, unreachable, 8 months into a mission built to run for 4 years and visit 2 more planets after this one, with no primary receiver left and a backup nobody yet understood. Then, the onboard software commanded the damaged backup a second time, on its own, and the link came back. Barely. Every attempt after that to revive the primary failed. It never worked again. Not once. Not in the nearly 5 decades since. Engineers tried more than once in those early years to bring it back, running every diagnostic the ground software allowed, and each attempt returned the same answer. Nothing. Voyager 2 has spoken to Earth through that same shorted, one-frequency backup receiver ever since. Through Jupiter, through Saturn, through Uranus, through Neptune, and out past the edge of the Sun, an emergency patch now in its 48th year. Here is what that damage actually costs, every single time anyone wants to talk to the spacecraft. Because the backup cannot drift on its own anymore, controllers have to aim their uplink to land within about 100 Hz of wherever its lock frequency happens to be sitting at that exact moment. The carrier itself runs near 2130.3125 MHz, better than 2 billion Hz, 100 Hz, somewhere inside 2 billion. Picture that carrier frequency stretched into a straight line the length of a marathon, 26 miles laid flat across open ground. On that scale, the window controllers have to hit would be smaller than a fingernail, somewhere along a course that takes hours to run. Miss it by even that much, and the backup will not lock onto the command at all. There is no second frequency to try, none at all. Something else was happening. That target does not even hold still. The receiver's lock frequency drifts with its own temperature, on top of drifting with the Doppler shift of two objects moving apart at several kilometers a second, the same way a radio left near a window can slide out of tune once the sun warms the case. Sources disagree on exactly how sensitive it is. One account puts the drift near 400 Hz for every degree, another closer to 96 Hz for every degree Celsius. Either number lands in the same place. A swing of a single degree, no more than the difference between a cool room and a warm one, can be enough to push the frequency clean out of that 100 Hz window. So the team never repaired the part. They built a ritual around it instead. Twice a week, controllers test exactly where the backup's lock frequency currently sits, so they always know where the narrow target has drifted to before they aim anything at it. After any command that might warm or cool the spacecraft's own electronics, they wait about 3 days for the temperature to settle before risking a precise uplink at all. Skip that wait, and the command can arrive at exactly the wrong 100 Hz and simply go unheard. No error message, no warning, just silence where a response should have been. Not a permanent repair, a permanent workaround run by hand on a schedule since the spring of 1978. 48 years of twice-weekly math now stand between Earth and a spacecraft that can only hear one frequency, drifting out past the edge of the sun. A tiny, moving target tracked by hand across billions of kilometers for longer than most of the engineers now doing the tracking have been alive. Nobody planned for the mission to depend on a calculation this delicate for this long. A shorted capacitor in 1978 was supposed to be a problem for that year alone, not a permanent condition of talking to a spacecraft at all. It was the first time this mission had come this close to going silent for good. It would not be the last. 48 years is a long time for a workaround to still be the only fix in the toolbox. But 1978 turned out to be only the first year this mission nearly went dark for good. The 21st century supplied 3 more chances, closer to the edge each time. The first came on January 25th, 2020. A routine calibration roll, a slow full turn meant to check the magnetometer's sense of direction, ran late on Voyager 2 for reasons nobody had planned for. The delay left 2 high-power systems drawing current at the same moment, more than the aging supply could spare. On a younger spacecraft with power to spare, that overlap would have gone unnoticed. On Voyager 2, running on a shrinking nuclear budget already stretched thin, it tripped the fault protection software into exactly the response it was built for. It shut down every science instrument running at the time, all 5 of them at once, to cover the deficit. Engineers had one chance to make the fix permanent instead of temporary. They switched off the primary heater on the cosmic ray instrument for good. A small, deliberate sacrifice of power the craft would never get back. The instrument itself kept working fine without it, cold and functioning both. By January 28th, the other 4 instruments were back online, and full operations had returned by early March. At the time, light took about 17 hours to cross the gap one way, so a full round trip, a command up and its answer back, ran to something like a day and a half. Nothing about this mission moves faster with practice. Every fix still travels at the same patient, punishing speed, whether the year is 1978 or 2020. The second call came in the spring of 2022, and it looks at first like something broken beyond fixing. Voyager 1's attitude control system, the subsystem that keeps its antenna pointed at Earth, started sending back telemetry about its own status that read as pure nonsense. Strings of numbers matching no configuration the spacecraft had ever used. And yet the rest of the craft stayed healthy the entire time, still pointed correctly, still returning good science, still hearing every command sent up to it. Only its own status reports had curdled into gibberish, a spacecraft that seemed to be lying about its own condition while behaving perfectly in every other respect. For months, the team worked the problem across the same day-long lag that slows every diagnosis on this mission. One guess tested, one answer waited for, before the next guess could even be tried. Engineers eventually traced the fault down to one quiet decision the subsystem had made entirely on its own. It had started routing its telemetry through an onboard computer that had stopped working years earlier. Not a broken sensor, a perfectly working system, faithfully reporting through a machine that was already dead. The fix took a single low-risk command, telling the subsystem to use the computer that actually worked. It resolved instantly. NASA announced it closed on August 30th, 2022. Why the system had started talking to a dead machine in the first place was never pinned down, only that it threatened nothing going forward. The third call, in the summer of 2023, was the closest of the three. On July 21st, a routine command sequence, the kind sent constantly without incident, nudged Voyager 2's high-gain antenna about 2 degrees off Earth. 2 degrees is nearly nothing, about the width of a thumbnail held at arm's length. But at roughly 12.3 billion miles away, a distance where sunlight itself needs more than 18 hours just to arrive, that sliver of an angle was enough to swing the dish's narrow beam clean past the planet. The spacecraft went both deaf and mute in the same instant. It could not hear a command. It could not send one back. Any other point in the mission, more than one dish on Earth might have been able to reach it and talk it back into alignment. Not this time. Voyager 2's own path past Triton in 1989, the maneuver that let it thread close by that icy, geysering moon, had bent its whole trajectory south of the plane every other planet orbits in. That single decision, made decades earlier for a completely different reason, now meant only one dish on the entire planet could even see the spacecraft from this angle. The 70-meter dish at Canberra. Not the network. One dish. For 11 days, that one dish listened to nothing at all. Wait. Then, on August 1st, Canberra's linked antennas caught something. Not a message. A carrier tone, faint and steady, with nothing riding on it. A heartbeat, and only a heartbeat, proof the spacecraft was still alive out there with its dish tipped the wrong way. On August 2nd, the network answered with everything it had. A 100,000 watt uplink out of Canberra, 5 times the power an ordinary command ever needs, aimed at the exact patch of sky where Voyager 2 should be listening. The press would call it an interstellar shout. The command needed about 18.5 hours just to reach the spacecraft, and controllers waited nearly 2 more days before they could confirm anything had worked at all. And then, everything changed. At 12:29 in the morning, Eastern Time on August 4th, 2023, Voyager 2 began streaming data again, right on its expected course, as if 11 silent days had never happened. The spacecraft had even carried its own fallback in case the shout failed, a command already loaded to reset its own orientation and try again on October 15th. It never had to use it. This is the move promised at the very start of this story, back when a far younger version of this same small team lost Voyager 2 completely and clawed it back with everything the network could throw. Nearly half a century later, the tools have grown, bigger dishes, more patient math, but the trick underneath has not changed at all. Point everything you have at one patch of sky and hope something out there is still listening. 3 incidents, 3 years, a power fault that blacked out every instrument at once, a spacecraft pouring out gibberish because it was still faithfully reporting through a machine that had died years earlier, a pointing error of 2 degrees that struck a probe deaf and mute for 11 days, 12 billion miles from anyone who could fix it by hand. Each time, the same small circle of people, working across a lag that never gets shorter, found the way back. Not by luck, by the same patient, unglamorous work that had kept this link alive since 1977. 2 spacecraft, 48 years old, held together this whole time not by some vast control room, but by a team small enough to count on your fingers. Half a century in, and the mission still runs on people, not machinery, catching every failure the machinery cannot catch on its own. It was easy, from the outside, to assume a fix like the interstellar shout came from an army of engineers working in shifts around the clock. It did not. It came from the same handful of names that keep showing up across every one of these rescues. Fewer of them than anyone watching from outside would ever guess. That handful has a number, and the number is smaller than anyone watching from outside would ever guess. 2 spacecraft are leaving the solar system forever. Fewer than 10 people are the reason either of them is still talking. Roughly 9 people run the Voyager mission today. Not 9 departments, not 9 teams, 9 people, and most of them have sat at the same desks since Ronald Reagan was in the White House. 6 of the 9 were already there during the long maintenance stretch that followed the Neptune flyby in 1989, years before either spacecraft crossed anywhere near the edge of the solar system. Nobody has published an updated count since a figure first circulated in 2017. So the number the mission still goes by is the same one, roughly 9, never a flat 10. Picture a mission like this, and the picture is probably wrong. Not a control room banked with monitors, not shifts rotating through the night. A short list of names, most of them decades into the job, working from ordinary desks. Larry Zottarelli joined Voyager at the 1977 launch and spent the next 39 years on the flight data system, the onboard system that packages every image and measurement before it is sent home. He trained his own successor before he finally retired in 2016, at 80, the last original Voyager engineer still on the job when he left. Edward Stone served as the mission's project scientist for 50 years, from 1972, 5 years before either probe left the ground, until he stepped down in 2022. Linda Spilker joined the imaging team in 1977, months before launch, then left for almost 30 years to work Cassini at Saturn, and came back to take over as project scientist the year Stone retired. Suzanne Dodd's first job out of college, in 1986, was writing the command sequences for the Uranus encounter. She returned to the mission in 2010 as project manager, and has run it ever since. These are not new hires learning an old machine from a manual. They are the hands that built parts of it, decades on, still at the same desks. Between the 4 of them, over a century of a single mission, spent on 2 spacecraft that never once came back for a tune-up. The knowledge that keeps 2 spacecraft flying does not live in a database, it lives in them, and where it doesn't, it lives in garages. During the mission's first 12 years, thousands of engineers rotated through the Voyager program. Nobody built a formal library to hold what they learned. So when they retired through the 1970s and 1980s, many carried their own boxes of schematics and wiring diagrams home. And some of that material still sits off-site today, filed nowhere but in memory. When the current team needs a document now, the first step is not a search. It is a manhunt. Work out who originally built the subsystem in question. Track down where that person's files ended up. Sometimes the answer is a second-hand microfiche reader, the projector machines old libraries once used to blow rolls of shrunken film up onto a screen, bought used off eBay because nobody has manufactured one in years. And sometimes there is no answer. The document simply does not exist anymore, and the fix has to be worked out fresh. From first principles, on hardware nobody alive helped design from scratch. The paperwork is only half the difficulty. In 2015, the team needed to hire a replacement engineer. The job did not call for a rare specialty, it called for an extinct one. Fluency in assembly language, instructions written by hand for the spacecraft's own custom 1970s processors. A skill the commercial software industry had abandoned decades before the posting went up. The only reason anyone still learns it is that 2 machines, 24 billion kilometers away, have never spoken anything else. A tool that shrinks by the year, kept in use by 2 spacecraft that refuse to stop needing it. Even once someone knows the language, the mission will not let them work quickly. A command takes 18 to 22 and a half hours just to arrive. The confirmation takes just as long coming back. One round of troubleshooting, a guess, a wait, an answer, can burn most of 2 days before anyone on Earth knows whether the first idea was even right. Spilker put the weight of it plainly. When a mission runs this long, she said, you start to regard the people on it like family. The team spans multiple generations now, and some of the younger engineers were not even born when either spacecraft left the ground. And when an instrument finally has to be switched off to save the last of the power, the loss reaches past the engineering. Spilker relayed that the engineer who had helped build the cosmic ray instrument in the early 1970s, and who still led it decades later, described turning it off as something close to losing a best friend. Not a system going quiet. A colleague, retired, 9 people, 2 spacecraft. A command that takes most of a day to arrive and most of a day to answer. That has been the entire operation for almost 50 years. Run not by an institution, but by a short list of names who happen to stay, and who built their own careers around never quite letting go. Every fridge bulb signal caught across billions of kilometers. every patch written in a dead language, every twice-weekly frequency check kept since 978. All of it traces back to this same short list of names. Take away the antennas and the record and the nuclear hearts, and what is actually holding two spacecraft together at the edge of everything turns out to be 9 people who never stopped answering the phone. The spacecraft still had years left to give. What they needed next was something no one on that shortlist could build for them. No one on that shortlist could build them a replacement. Not from spare parts, not from a bigger budget, not from technology that has existed for decades longer than either spacecraft has been flying. So it is fair to ask why NASA does not simply send something newer out to take over the watch. Nothing about 2026 engineering says it couldn't. The honest answer starts with everything a new mission could do that Voyager never could. A modern Voyager would carry computers millions of times more powerful than the 6 machines still running the originals. Its memory would multiply out to something like 200,000 times what launched in 1977, a jump so large that the entire brain of both current spacecraft, combined 68 kilobytes in total, would fit inside a rounding error on a single modern chip. Its instruments would be a full 40 years more advanced than the ones still limping along today. One claim about a modern mission gets repeated often, that it would return 1,000 times the science. It does not trace back to any real study. The honest version is quieter, vastly more capacity, sharper instruments, not a tidy multiplier. Instead of a radio no stronger than the bulb inside a refrigerator door, a new mission could talk in light instead of radio waves. NASA's Deep Space Optical Communications Terminal, riding along on the Psyche spacecraft, reached a peak download speed of 267 megabits a second. And on December 11th, 2023, it streamed ultra-high-definition video home from more than 19 million miles away. Call it Netflix, beamed in from past Mars. At 240 million miles, the same link still held several megabits a second. And on December 3rd, 2024, it set a new distance record, an optical connection working across 307 million miles. The demonstration wrapped that September, having sent 65 downlinks and 13.6 terabytes home, its last signal arriving from 350 million kilometers out. Light like that can carry data 10 times faster than radio of the same size and power. Some estimates put it at 100 times faster. That should make Voyager's whisper of a radio look obsolete already. It doesn't. Even DSOK's longest link, the record-setting one, sat roughly 1,000 times closer to Earth than Voyager 1 sits right now. Making that connection work also needed a purpose-built telescope on the ground, something Voyager's radio has never once required, staring at one point in the sky, waiting for a beam of light to find it. Nothing carrying data on light has flown anywhere close to where Voyager already is. Not within 1,000 times of it. Speed is coming too. A proposed interstellar probe, backed by the NASA and Johns Hopkins, would ride a solar sail, a thin mirror pushed forward by sunlight alone, out at about 14 astronomical units a year, roughly 5 times Voyager's own outbound crawl. That is not a concept stuck on paper either. Japan already proved the idea works. In 2010, its Icaros spacecraft picked up about 890 miles an hour from sunlight alone. No engine, no fuel, close to a commercial airliner's cruising speed, gained entirely from photons pressing against a sail, unrolled in the vacuum of space. Breakthrough Starshot goes further still. On paper this time, a laser-driven sail meant to push a gram-sized probe to about 20% of the speed of light, fast enough to reach Alpha Centauri in roughly 20 years instead of the tens of thousands it would otherwise take. And a modern probe could think for itself. In theory, the fault protection flying today, even on a mission as new as a Europa Clipper, still works the way Voyager's does, watching fixed thresholds and firing preset responses when one is crossed. There is no engineer riding along, and there does not need to be, because the logic is the same logic that has run on Voyager since 1977, just newer hardware underneath it. Software that can genuinely reason through a failure no engineer ever anticipated, the kind of judgment call the 9-person Voyager team makes by hand across a 2-day round trip, exists only inside NASA's research labs. None of it has left the ground. So the 2 most advanced ideas in deep space communication and propulsion already exist. They already work. and neither has come anywhere near replacing what launched in 1977. What will finally end Voyager, then, is not a rival technology arriving to take over, not a faster probe pulling even, not a smarter one catching up from behind, a block of plutonium decaying quietly since before laser communication or solar sails or any research lab's version of a thinking spacecraft ever existed. Every year, that block gives off about 4 fewer watts than the year before. That decline was set in motion the day the plutonium was cast, before Psyche, before Icaros, before anyone had written a line of the code now being tested to replace a human's judgment. Not a flaw a modern engineer could patch. Not a part that could be swapped out on the next servicing mission. A fixed decay curve, running since before either spacecraft left the ground, indifferent to whatever gets invented next, and only now, finally catching up to both of them. No new mission changes that math. The next planetary alignment that could send something else chasing after the Voyagers will not arrive until the 2050s. Decades past the point, either probe is expected to fall silent. Whatever answers that call someday, it will be following 2 spacecraft that were never really waiting to be replaced. They were only ever waiting to run out. That countdown is real. It is short. And it is not where this story ends. 2 probes built in workshops of the 1970s were designed to survive 5 years each. They have run for nearly 50. Not luck, not chance, just engineering. Still working, 5 decades on. The mission was funded to end Saturn. It never did. Voyager 2 kept going, onto Uranus and Neptune, worlds nobody had budgeted a single dollar to visit. Nobody planned for either machine to still be transmitting from beyond the planets at all, let alone from interstellar space, closing in now on its own 50th birthday. 10 times the design life, 10 times the promise stamped on the original paperwork, and still, somehow, answering. The same slow nuclear decay that has kept both spacecraft alive this long is the exact same clock now counting down what they have left. The end, when it comes, will be physical, and it is close. Power on both spacecraft falls by about 4 watts every year, the same steady bleed that has run since each generator was first sealed shut. On February 25th, 2025, Voyager 1's cosmic ray subsystem, the instrument that once heard the plasma bell ring at the true edge of the solar system, went dark for good. About a month later, Voyager 2's low-energy charged particle instrument followed it into silence. One by one, the instruments that once mapped volcanoes on Io and rings around Uranus are being switched off, not because they broke, but because there is no longer enough power left to run them. The plan now is to keep at least one instrument alive into the early 2030s. No single year is fixed. Engineering telemetry, the plane signal confirming a spacecraft is still there and still pointed the right way, might hold until roughly 2036. The last working science instrument is expected to go dark sometime in that same decade. The team hopes to reach the 50th anniversary of launch, and maybe a little past it, 2028, perhaps 2030, but probably not much further than about 5 more years before the power finally runs out. Or something else simply breaks. Not a hard deadline. A narrowing window, closing a little more with every watt the generators give up. Nobody can say which it will be. Nobody has to. Both endings were written into the mission's design the day its nuclear hearts were built. The same faint fridge bulb signal that has been crossing billions of kilometers to reach Goldstone and Madrid and Canberra will fall silent along with everything else. And the same handful of people, the roughly 9 engineers who have nursed this link through every dead computer and shorted capacitor and mispointed antenna, will most likely be the ones sitting in the room when it finally happens, whenever that turns out to be. Not a large team for a mission this old, or this far from home. Just the same small number of people, still showing up, still listening, right up to the end. But losing the signal will not stop the flight. Both spacecraft are still moving outward, about 17 kilometers every second, and they will keep moving long after the last engineer stops listening. Voyager 1 is heading toward a pass within about 1.6 light years of a star, called Gliese 445, in roughly 40,000 years. A light year is the distance light itself covers in a single year, so 1.6 of them is a trip light needs about a year and 8 months to finish. Voyager will need 40,000 years to cover that same ground. Voyager 2 is aimed toward Ross 248, passing within about 1.7 light years of it on a similar timescale. Neither spacecraft is steering toward these stars on purpose. They will simply drift near them by chance, still moving, never landing, never stopping, then continue on past into the dark beyond. 40,000 years is longer than any painting left on any cave wall by any human hand. Longer than agriculture, longer than cities, longer by a wide margin than anything anyone has ever written down. By the time either spacecraft reaches those stars, its power will have been dead for thousands of years already. Every instrument silent, every heater cold, no one on Earth still listening, or needing to. The one thing still working, riding on the outside of each spacecraft, will be a gold-plated disc that never once needed a watt of power to keep going. It's a record that needs no power to play. It's a record that needs no antenna to be heard. It's a record that needs no one alive to still be true. And it's the only thing left aboard either spacecraft once everything else this mission ever built has gone quiet. Its cover still holds the map to find the sun, and the slowly decaying sample that could tell a stranger how long it has been drifting. Long after there is anyone left on Earth who remembers building it, it still carries what it left with. Ocean surf, thunder, birdsong, a small boy's hello, recorded for the occasion, a heartbeat, taped in the days after two people agreed to marry, greetings spoken in 55 languages by people who once lived on this world. It carries the story of everyone who has ever lived on this small planet, drifting outward long after the last person who built it is gone, long after the last dish on Earth has stopped listening for anything at all. Two machines kept alive against physics, on a clock that physics itself would never let them reset, are finally closing in on that clock's edge. That is not a tragedy. It is simply what it always meant to build something this small and send it this far for this long. Thanks for joining me on this journey through the most improbable signal humanity has ever kept alive. If you found it as remarkable as I did, a like or a subscribe helps this channel keep finding stories like this one. Two machines, 9 people, and a golden disc, still finding each other across billions of kilometers of dark. It takes real time and real care to trace a story like this one, all the way from a summer student's calculation in 1964 to a whisper still arriving from beyond the edge of the solar system today. And remember, the next time you look up, somewhere past the edge of the only home any of us has ever known, 2 golden records are still turning, carrying every voice that ever said hello into a silence that has not answered yet, and may never need to.